So I think we had started off with the timing considerations, right? And we will try and we will continue with that explanation. Okay, few of the concepts are already seen. So if a question is asked what is meant by timing, then it is nothing but responses to inputs are not really immediate but occur after some appropriate time delay. So this is nothing but called your time delay, okay, or timing consideration. So why is it so important? In order to understand as to how this time is maintained between the input and the output signals. So to achieve desired responses, which means I want my systems to be faster, right? And we have seen these propagation delays, right, which is moving from low to high and from high to low. Students, I think you can recall these concepts, isn't it? What is meant by propagation delay from low to high? Can one of you unmute and respond?
Like when the input signal is shifting from the lower level to the higher level, there would be a delay in the time taken. So that's
Exactly,
called
exactly. So that is nothing but my propagation. Propagation is nothing but movement from one point to another point. So when it says LH, then it's low to high. When it says HL, then it's from high to low. Okay, so it's as simple as it is. Right. So these were the diagrams, we actually saw, and I have adopted these diagrams from your prescribed textbook, which is Gibbon. Okay, Donald Gibbon. So let's assume that this is your S and this is your R, and these are actually output responses of your SR latch. Okay, so I can see that this midpoint, when I take a line, it's actually appearing here. This midpoint had to be appeared here, but then there is a slight shift. So this shift is nothing but called TPLH. So it's moving from low to high. So I label it as TPLH. Okay, and similarly, when I see that opposite for my Q bar, as you all know, Q and Q bar are opposite to each other. So it corresponds to TPHL, which is from high to low. We have already seen these. Right? Okay. Similarly, okay, we will probably we even saw as to how these timing diagrams are, enabled, or how we get these timing diagrams. So a question can be asked using SR latch. Okay, draw a response waveform along with the respective truth table. So what you have to do, you have to know what is the truth table for your SR. Okay, and accordingly, remember we had done gated SR latch, S bar R bar latch, right? So the SR latch we had seen with enable, isn't it? So that truth table has to be considered, and you can draw these diagrams. Propagation delays from high to low and low to high are assumed equal. So we assume that when it is moving from low to high, it's taking the same time for the propagation from high to low. When S and R is equal to 1, then Q bar becomes 0. Okay, so when it is high, it is not needed, right? That particular state is not needed by us. So you can see that each timing, okay, each dotted line is actually given or named T1 to T17. Okay, T1 to T17. So what is happening here? We can see that at every instant of time, okay, it can be either the rising time or the falling time. Okay, I have made sure that these dotted lines are there. So accordingly, what is going to happen is we are even putting dotted lines for this R input. Okay, highs and lows, all the highs and lows. So we can take these dotted lines as our reference, and accordingly we can check for Q. Okay, so when S is 1 and R is 0, I am getting 1. Okay, so till the value changes, okay, till the value changes, the value is maintained up to this point. So once it becomes 0, Okay, 0 at this point, 0 and 1, then a 0. So which means there is a small delay here that you can see, right? So accordingly, you can actually justify as to how you're getting your Q and Q bar. So Q and Q bar will be opposite to each other. Okay, will be exactly opposite to each other. Fine. So students, is there any doubt as to how we are getting this waveform? It is just as per your uh, truth table of SR latch. We have seen this in the previous class as well, right? Okay. So now there is one typical case, okay, which I have highlighted here, T15. So at T15, you can see both S and R are actually changing their states. They're changing from high to low, and here also from high to low. So at this point of time, we are going to get, some kind of response, okay, which is actually a glitch. Okay, response of latch is unpredictable. So remember when we had uh, the star written, right? So that is nothing but called your unpredictable state. So I hope you are able to follow as to what I am trying to say. Okay, so just a moment, I will show you. So that will be easy for you to understand. Yeah, see, this is the state that we are talking about. Okay, this is the state. So this is our SR, S bar, R bar. We will look into, yeah. So see the state when both are actually changing simultaneously. Okay, so we are getting something called unpredictable state. Okay, unpredictable state, and this is referred to as your toggling state. Okay, so I do not want this kind of response. Okay. Right. So any doubt here, students, as to how we are getting these waveforms? If any doubts, please ask. We can revisit them. Yeah. Can I proceed?
Yes, sir.
Okay, fine. So this is, with respect to your waveform, okay, just have a look at it and compare your truth table.
Excuse me, sir.
Yes, tell me.
Sir, if it's unpredictable, why provide an input then, sir?
Unpredictable?
If it's gonna be like, if the output is gonna be unpredictable, then
why are we giving the
provide
input?
an input. Yes, sir.
See, your Nikhil?
Rohit, sir.
Rohit, okay. Rohit, see, the point here is we have to give all the combinations. Just because this gate is giving me an unpredictable state doesn't mean that I shouldn't give this combination. Is there any way that I can change 2 raised to 2 is equal to 3? Can I make it 2 raised to 2 is equal to 3?
No, sir.
Not possible, right? So I have to give all my combinations 0, 0, 0, 1, 1, 0, 1, 1. Okay, either the latch response or not response. It is my duty to give all the levels of inputs. Okay, and then we will characterize and we will say this gate isn't working for this input. This gate isn't working for this input. So that is how we proceed with our analysis. Is that clear, Rohit?
Yes, sir.
Okay, fine. So now that we have understood, how we get this timing diagram, the easiest way that you can do is, as I've done here, you can take the dotted lines. Okay, for S and R, you just put the dotted lines, you scale so that you will get proper straight lines. And you will be easily able to put the waveforms for Q, and of course it's going to be the opposite for your Q bar. So here what you can see is, you can keep your truth table as a reference here and just map those values to your waveform. So if it is giving 0, then you can put a low value. If it's giving 1, then you can give a high value. So accordingly, you should see here what is here 1, 1. So in our SR latch, it normally follows our value of S. Okay, majority it follows the values of S, and there is a little bit of influence of R as well. Okay. Okay. So the next main important concept that you will be looking into is minimum pulse width. Okay. So this is very much important, just like the concept of your threshold voltage. So when it reaches about 0.7, that's when the transistor turns on, right? So similarly here also, you can find that if it doesn't match to that minimum requirement, then I cannot call it a high value. Then I cannot call it a low value. Okay. So if some value is about 0.5, okay, I want 0.7. So can I consider it that my transistor is turning on, students? If my value is 0.5.
No, sir.
Yeah. So which means we are waiting for a particular value. Okay, we are waiting for a threshold value. So similarly here, I will have a minimum width for each wave. So if the wave is having this time duration, then only I will consider that it is a low value or a high value. Anything less than that, okay, what I'm going to do, I will neglect that. So we have seen these kind of effects in our switch debouncing circuits, right? We have seen those contacts, right? When the contacts happen, then we are seeing a lot of spikes. So those spikes are nullified with the help of our SR latch, isn't it? Okay. So here now we will look into the minimum pulse width. Okay. Another specification stated by manufacturers of latches is the minimum pulse width. So TW, okay, width, time period, width, minimum. Okay. So width in terms of time and the minimum value. Okay. So minimum amount of time that a signal must be applied in order to produce a desired result. So that's the minimum criteria. It should have so much of width. Then only I can say that it is a high value. Then only I can say it's a low value. Failure to satisfy this rule or constraint may cause unintended change to have or have the latch enter into metastable. So what is metastable? As we have discussed previously, it goes into which state? It goes into the toggling state. Yeah. Okay. Okay. So now you can look at this diagram here. Okay, I have S. So the minimum. Okay, so what I'm taking the midpoint from here. Okay, so it will be in terms of numbers. Okay, so I cannot say that I'm going to take the midpoint from here and the midpoint of the rising edge or the slant line. Okay, so minimum specifications will be given by whom? By the manufacturer. So they will say if it's 0.3 or it's about the time period, they will give it. If it is so much seconds, then only you consider. If not, then we are not considering it. So that is the minimum requirement. Okay, so you can see that here your minimum pulse width is so much. Okay, here the minimum, okay, is so much. So the same, if you can calculate using a scale, okay, the time taken for the waveform to reach from this point to this point becomes the same. So here we can see that for your R value, okay, I have low and then it's going into high. So after some time, okay, after the minimum time width, okay, what is happening? The state is changing. Before that, the state isn't changing. Why? Because it has not crossed the minimum value. So once the minimum value is crossed, then you can see that the value is changing. Okay, so I hope you can understand, right? So what we will do here, just draw or extend the line. Yeah, so at this point, after it reaches this point, then only you can see that the changes are happening, right? These changes are reflecting. So it's moving from a low value to a high value. So this value is actually propagating here. Okay, and here it has reached low value. Okay, but then it's waiting for the response of R. So look at this point. Okay, look at this point. So once it has reached this point, then only the low value is coming up here. The low value is coming up here. So students, you're able to understand. So it's waiting for a minimum value. So once the minimum value is satisfied, then only the changes are happening where? In Q. And the opposite happens to Q bar. Any doubts here, students? Any doubts? Can I proceed?
Yes, sir.
Okay, fine. Okay, so the next one that we will be actually looking up into is your setup and hold time. Most repeated question. Many times it's going to be asked in your exam point of view. What is setup time and what is hold time? Okay. Consider timing diagram for a gated D latch. Okay. Now, how does a D latch work? Can someone tell me? How does a D latch work? Whatever is the input, is it passing or is it getting inverted at the output? D latch. Remember, we had seen that in our previous classes. If my input is 0, what is going to be my output in D latch? Yeah, students.
So it will be 1.
No. No. D means delay, right? So which means whatever is the input, it is delayed by a certain amount of time. So which means whatever is the input is the same across your output. Okay, fine. So now let us get into the explanation. Consider the timing diagram, okay, for gated D latch, and I have given two combinations here. Okay, so just have a look at it. So here you can actually see that you have Q output which follows the input signal D. So that is how your D latch works. Wherever the enable C is equals, yeah, fine. So we are giving an enable signal. If I'm disabling the signal, then what is going to happen? The outputs are not going to come up. Okay. So Q output follows the input D whenever the enable signal C is equal to 1. When C is equal to 0, the changes are ignored. So whatever changes are happening, that is nullified whenever C is equal to 0. So let us look at the diagram here. So input is 1. Okay. So it is waiting for my C to turn on. Okay. So once it is high, then immediately it will check for value which is in D high. So that will come up here in Q. Then at till this point it is 0. So when C is equal to 0, whatever changes are happening, those are not reflected here. Okay. So which means the same high value is continued, okay, till it sees another high value here. Okay. So this is enabled here. So once this is enabled, what is happening? You can find that this low value is coming here. Any doubts here, students? Students, any doubts here?
Sir, could you repeat once more?
Once more. Okay. Fine. Now we know that the value here is 1, isn't it? We know that the value here is 1. And here what I'm doing is, the rule is that it is going to wait for my enable signal. So here I have my, at this point I have my enable signal. So there is a small delay actually. Okay. There is a small delay, and whatever is the value there, okay, the high value, that will come up here. Okay. So that is happening. It is waiting for the enable signal to be high. So once the enable is high, there are two rules. Okay, check for enable signal if it's low or high. If the value is high, then it will check for the value of D. So D value will come as the output. If the value is low in enable, then whatever changes that you are seeing here, that is not reflected. Instead, whatever values were there previously, the same thing will be continued up till it sees another enable signal. Understood? Understood? Now let us see here.
Yes, sir.
Yeah, let us see here from this point to this point. Actually, what should have happened? Now the value is changing from high to low, right? It's changing from high to low. But here, what do you see? Do you see that change is happening? No. Instead, the same high value is continued from this point to this point. Same high value is continued, which means there is no change in the value of Q, right? There is no change in the value of Q. Now next it will look for something else. It will look for a value, okay, for another value here, okay, which is going high. So this is going high. Next it will look for the value here, which is 0. Okay, since it is high and the value is 0, this value will come down here. That's my Q. Okay, so first rule, check for C. Second rule, see what are the values of D. If C is high, okay, then only the values of D will come to Q. If C is low, then whatever values was there previously with D, the same values will continue. Okay, same values will continue. Okay, so just you can understand that whenever C is high, then changes happen. Okay, so there is a change. Okay, so there is a change happening. Whenever there is 0, the same value is continued. So that is what you have to remember with this waveform. So I think now it's clear for all of you as to how we are getting this waveform. Is it clear, or students, should I explain it again? Is it clear?
Sir, but which is the whole time, sir? Like in the whole graph, which is the whole time?
I will. Now, whatever I explained, did you understand till there?
Yes, sir.
Till there understood? Okay, fine. Now let us look into setup time and hold time. Okay, now I will come to the explanation. Consider times T3, T6, 11 and 14. So 3, 6, 11, 14. So all these are highlighted. Okay. C is returned to 0, which means C is changing to 0. Output latches onto its current state. What is the current state? 1. So output is remaining the same value. To guarantee latching action, constraint is placed on D signal must not change right before C goes from 1 to 0. Okay. So one condition here is that whenever this change is happening, okay, the value of D also should be continuing. Okay, that is a small condition to be maintained. Now we will get into the explanation as to what is setup and hold time. Setup time, the minimum time, okay, TSU, okay, SU is setup, H is hold. So SU is setup time. So the minimum time that the signal must be held fixed before the latching action. Okay. So what is the minimum time that your signal should be kept constant before that value is passed to Q? Okay. So that is nothing but meant by your setup time. Now the hold time is the minimum time that the signal must be held fixed after the latching action. Okay. So which means here you can see the first half. Okay, the first half is your setup time and the next half is going to be your hold time. Okay, so this blue that you see here are having two halves. So the first half that you see is setup time and the next half is called hold time. Now what is happening here? In the setup time, the value is maintained. Okay, and in the hold time, what is happening? It is waiting for the latching action. So this one started before latching action, right? So which means what is latching action here? What is latching action? The value, okay, the value of C getting changed. Okay, so setup time will make sure that the value is held fixed before. Okay, so setup is happening before. So setup is here. Okay, this is setup, and this side is hold. And at this point exactly is where the value of my control signal is going from high to low. So the first half is referred to as your setup and the next half is referred to as hold. Okay, so setup is actually preparing the signal. Okay, setup is preparing the signal. Hold is maintaining the value of whatever was set up in the previous timing. Is that clear?
Sir, so setup and hold times are only concerned with the enable signals.
Exactly, right? So they are only concerned with the enable signals when it is moving from a high value to a low value, because that's when it needs to maintain the same value here, right? It should not change the value. If it changes the value, then this current state has to be maintained, right? The current state has to be maintained. So that is nothing but called your setup and hold. So why are we doing this? So that we get stable outputs. So I can say that this is my minimum width, and the minimum width has to be maintained. If it's not maintained, then I'm nullifying it. I'm not considering it as my valid input. Yeah, is that clear, students?
Yes, sir.
Okay.
Yes, sir.
Yeah. So we will see another section here, which is an unpredictable state. Okay, so something which is unpredictable, which means it is not needed. Okay, that particular value is not needed. So I have D values moving from 1, 0, 1, 0. Okay, as usual, it's just moving on. Then I have my enable signals, okay, which is going from 0, 1, 0, 1, 0, 1, 0. So now I have to check for Q values. Fine, till here what is happening? It is all 0. Okay, so the previous state is all maintained. Then here it is going with high. Okay, so once it goes with high, the same value, whatever is in D, is taken up, and it's still high. Okay, so which means it is still checking for D. So high is here, and then this high comes up here. Okay, now here, this is very important. Here you see your setup and hold time. So setup is nothing but your first half, as I told you. Hold is your next half. So that same value is retained here. Okay, so which means when your enable is going down, it's having TPHL, okay, from high to low, then what's happening? The same state which was there previously is continued, okay, and it will look for another high state. So once it's high, it will look for D, and the same value will come down here. Now there is one unpredictable state here. Your C is also changing from high to low, and your D is also changing from high to low. Okay, so this shouldn't happen. Both of the inputs should not change at the same time. If in case it changes at the same time, my Q output will not be stable. I will get 0 and I will get 1. I will get 0 and I will get 1. So which means there is a toggling effect that happens. So this is called an unpredictable response in a D flip-flop. Okay. Sometimes your gated D latch is also called D flip-flop. Is that clear, students? So your gates should be able to track small changes. It should not be able to. There should not be changes on both the side, control as well as input. Okay. So here you can see it's happening at the same time, moving from high to low, and from here it's moving from high to low. So which means at this point it will maintain the high value. Okay, and then here in order to maintain the high value, okay, this has also changed. Your input has also changed. Okay, so it is a kind of, it needs to stay high, it needs to come low. Okay, because of the variations in your enable as well as your D flip-flop, D input at the same time. Okay, so you will see these kind of unpredictable states in most of the time. Okay, most of the gates, most of the latches, where changes should not be simultaneous. Is that clear, students? Yeah.
Yes, sir.
Okay, fine. So we will continue, okay, with our next session, okay, which we will be looking into a few more options, okay, which is a few more topics, okay, which is going to be your flip-flops. Okay, so before we move on, to the next topic, you will have to know what is a flip-flop, okay, and what are its respective truth tables. So that is, very much important. So here you can see for your SR flip-flop, okay, whenever it is 0, 0, the same thing, whichever was there previously, the same is taken up as the output. Whenever it is 0, 1, then the output is 0. 1, 0, the value is 1. Whenever it is 1, 1, it is invalidated. So I think this up till here, you all know as to how this works, isn't it, students? Yeah. So this is your truth table for your SR flip-flop. So any doubts here with this truth table? Okay. So the next thing you will be needing to know is about the characteristic table. I will tell this in the next sessions. As of now, I want you to know only the truth table. If possible, quickly, you can make note of it. Clock is 0, then whatever is your input, it's a don't care, and your output is going to be the previous state, whatever was there, that has been continued. Whenever the clock is enabled, so the D changes are maintained, okay, just like how we saw in the waveform in our previous session, right? We saw using the waveforms. So 0 is 0, 1 is 1. So this is for your D flip-flop. Next, talking about your JK flip-flop. Okay, JK is nothing but your Jack Kilby. Any idea as to who is Jack Kilby? Yeah.
No, sir.
Huh? No. Okay.
No, sir.
So he was the one who actually invented your IC. Okay, your integrated circuit. So JK, okay, you have two inputs here, 0, 0, 0, 1, 1, 0, 1, 1. Okay. So similarly here also, whenever clock is 0, the same memory state is contained. JK, whenever it is 0, then memory is taken 0, 1, 0 is taken 1, 0, 1, 1, 1, whatever was Q here, okay, Q, suppose it was 0, then here I'm going to get 1. If this Qn was 1, then I'm going to get 0 here, okay. So this is your JK flip-flop. Then your T flip-flop, okay, T is nothing but your toggle flip-flop. So whenever you have clock 0, then the inputs are nullified and the memory is taken as output. Whenever the clock is high, that's when T inputs are considered. Okay, so it is 0, then Qn is there. Whenever T is 1, then Qn becomes Q bar. If Qn is equal to 0, then Qn bar will be 1. Okay, toggling state. So whenever it is high, it will go to the negated state. So any doubts here, students, with the truth tables of all these 4 flip-flops? Any doubts? Okay. So we will continue, our discussions in the next class, where we will be looking into characteristic equation. Okay, we will be looking into excitation table, and then we will also be looking into the master slave flip-flops. Okay, edge triggered flip-flops. So all this we will be looking into. So as of now, I want you to know just the truth table of all these 4 flip-flops. If possible, try to make a note of all these 4 flip-flops: JK, SR, T, D. All the truth tables are needed. Okay, so make a note of these, and then we will continue our discussion in the next class. Okay, students, can we stop here? Okay.